Okay, so this is a problem in 3 parts that starts by using conservation of energy, including conservation of rotational energy, and then moves on to actually using Newton's second law in rotational form. And it's supposed to highlight the limitations of using conservation of energy. In other words, when you can use conservation of energy and when you can't. Okay, so step 1 is going to be use conservation of energy and that's going to be to find the velocity of the yo-yo at the ground. So to find the velocity of yo-yo at ground. Okay. Step 2 is going to be to calculate torques acting on the yo-yo, which is not going to be terribly complicated in this case, right? So the actual torque computations are straightforward, which is the case in all but the most complicated problems. Okay, and then third, use Newton's second law in rotational form to find forces. Okay, forces and accelerations, or accelerations and forces in that order, looking at parts B and C. Accelerations and forces. Okay, so now let's actually read the problem. So we have a rudimentary attempt at a yo-yo, in this case simply a cylinder with string wound around it. Wouldn't work all that well. And it has a certain mass of 0.43 kilograms, and it's released a certain height above the ground. Okay, so basically you have wound string, and there's plenty of string that we're not going to run out of string before you hit the ground. The ground is down here. Okay. So we want then to say, okay, well obviously the yo-yo is going to pick up speed. If it wasn't for the string and we just dropped the yo-yo, it would fall like a particle in the absence of air drag or anything. And so it would just accelerate like any other projectile. And so we could find the velocity when it hits the ground, either using kinematics or using conservation of energy. And it's actually true too here. Now, question A asks for that final velocity before we hit the ground. We're going to solve that using energy, right, as step 1 indicated. Now, we could actually go ahead and take the route that we have to for questions B and C, which asks about acceleration and tensions, and find the acceleration of the system, and then use kinematics to find the final velocity when it hits the ground. But that would be more complicated, and it wouldn't show us what we can do with energy, because energy is a simple way of solving problems, but it's only good for certain things. What energy conservation is good for is solving for final positions and final velocities. In part A, asks for a final velocity. Also, it's good for solving for initial positions and initial velocities. Okay, so we're well within the bounds of what energy conservation is good for. So we're going to use E1 equals E2. Our two energy states are going to be here. This is E1 at release, and then E2 upon hitting the ground. Okay, so what that's going to look like? Well, we release the yo-yo from rest, right? Release from rest. So we have no kinetic energy to start with. We do have potential energy. So the E1 side of the equation is simply going to be mgh. That's it. Okay? When we hit the ground, we've used up all of our potential energy, because we're going to define our coordinate system such that down here we have y equals 0, and up here we have y equals h. Okay? y equals h. Okay? And so when we hit the ground, all kinetic, right? But what form does that kinetic energy take? Well, it has two terms, the rotational kinetic energy and the translational kinetic energy. All right, so we're going to have 1/2 mv center of mass of the yo-yo squared plus 1/2 I, the moment of inertia of the yo-yo, omega squared. Okay, That's the key to all these types of problems that involve conservation of energy when there's a rotating object. In this case, the object is both rotating and translating. There's just one object doing both. This basically is like a rolling motion problem. And so it's fair to say that a yo-yo is essentially a vertically rolling object. So I can say here, note, yo-yo motion is essentially vertical rolling. Because that string is like the ground that supplies enough friction so it doesn't slip. So vertical rolling, just like with rolling without slipping on flat ground, or sloped ground for that matter. Okay, all right, so let's then move on. And what we need then for, just like in a conservation of energy problem that does involve rolling, we need that relationship between the velocity, the translational velocity of the center of mass of the yo-yo, and the angular velocity of the yo-yo. Okay? And by the way, here is the center of mass at the geometric center. Okay? So the relationship is simply that V center of mass, is omega r. Okay? And right, I just want to see if we define a big R or a little r, and I'll use little r. Okay? All right. And you'll see it's not going to be an issue about the fact that we don't have a value for it. It won't come up. Okay? Or in other words, it will cancel. So then what this is going to look like when we now make that substitution for V equal to omega r, well, now we're going to have mg h equals 1/2 m, okay, what I'll just call V, dropping the center of mass, now that I've called attention to it, because that's the only translational velocity we care about. We're not asking about translational velocities along other points of the yo-yo anywhere in the problem. Times 1/2, okay. We're going to say it's a simple cylinder, okay, so that we're going to use the moment of inertia of a simple cylinder, which is 1/2 mr squared. All right, so that's our I. And then omega is simply going to be V over r, so we get our V over r quantity squared. All right, so you can see our r's cancel. All right, so now we can combine our like terms on the right-hand side of the equation. So, our m's are going to cancel as well. So you might wonder why were we even given it? Well, we were given the m to answer part C of the problem, the tension. Okay, so then we're going to have that GH is going to equal 1/2 V squared plus 1/4 V squared. So that's going to be 3/4 V squared. And so then when we actually solve for V, it should be 4/3 of GH all inside the square root. And it's definitely worth pointing out an important relationship here to previous material. If this had been just a dropping object, like dropping a block or dropping a ball or something, and there had been no rotation, then this whole second expression wouldn't exist, and instead of 4/3, it'd be 2gh, right? And we've seen that result. And so it would be the final velocity after free fall would just be the square root of 2gh, however far it falls, right? Then it speeds up. And whether it's on Earth or not depends, it gives you your g. So then, well, 4/3 is smaller than 2. Well, why is that? Well, because it's going to be moving slower in the translational sense, because some of the energy that would have gone to just speeding up the ball as it fell is instead having to go to actually rotating the yo-yo as it falls, because it's spinning as it falls. It's doing the yo-yo motion. So that means that it will actually be moving slower. Okay, so let's plug in our numbers. Okay, so we got the square root. So second for square root function. All right, 4/3. All right, multiplied by 9.8. Multiplied by our h, which is 0.75, 75 centimeters. Okay, 31.3 meters per second. Nope. I was like, that's too fast. All right, there we go. I left off a decimal. Okay. So. Okay. There we go. 3.13 makes a lot more sense. To fall pretty far to get up to speeds of 31 meters per second, which is like, high freeway speeds, 80 miles per hour or so. 3.13 meters per second. All right, great. All right, so that was, I kind of got sidetracked by talking about the steps, but actually that was solving for part A. Okay, so now to solve for part B and part C, that's where we're going to have to use these other steps, steps 2 and 3. Okay, so moving on to part B, which asks for the acceleration. Well, we can't use energy for acceleration. Okay, so cannot use conservation of energy to find an acceleration. You can't use conservation of energy to find anything like how long it takes for a process to happen. And since an acceleration is kind of synonymous for finding out how long something happens, because in fact, if you do know the acceleration and the initial conditions, that is the initial position, initial velocities, then you can exactly find out how long it takes for something to happen. And those are just the type of questions you can't answer with energy, because energy just doesn't look at the continuous process of the motion. Instead, it just looks at endpoints, and so it just doesn't tell you anything about the actual rate of change. All right. Okay, just do some resizing so we can get it all fit. And we want to find okay, so let's calculate torques. All right, so step 2, calculate torques. Well, what are our torques? Well, we've got two forces. We've got the tension force here, and we got the gravitational force. Okay, and well, what's our pivot point? Okay, well, our pivot point is going to be the point about which the object spins. So it is the center of mass. Okay, so that is our pivot. Just like with rolling motion, we want to choose our center of mass to be the pivot. I mean, there are times if something's rolling and it's just rolling a short distance, you can choose the pivot point to be the contact with the ground, and then you just have to calculate your torques differently, because it absolutely is a choice. It is a choice. But here it makes sense to choose the center as our pivot. And as long as you're consistent, then you'll get values that make sense with your given choice. Okay? So when we look at that, we can see right away that the gravitational force is not going to create a torque. So Tg equals 0 because R equals 0 for the gravitational force. Okay? So no torque caused by gravity. So the only torque is caused by tension. All right. So the torque caused by tension is going to be the tension force times the radius of our yo-yo, which we're using little r for, times the angle between them, which is just going to be sine of 90, right? How do we know it's 90 degrees? Well, if we look at the radius being right here, right, this being r, then we can see that the angle between r and t is 90 degrees. Okay? So that single torque is going to create our angular acceleration. So that's going to be equal to I alpha by Newton's second law, because that says tau net is equal to tau sub t. It's equal to the torque caused by tension. It's the only torque in tau. Okay, so now I just want to solve for alpha. All right, so then alpha is going to equal, okay, so the tension force times R, okay, and then divided by 1/2 m r squared. But we were not asked for the angular acceleration, we were asked for A, okay? And so what we want is the relationship between acceleration and alpha. So A tangential, all right, is going to equal, and that's of the center of mass. It's the only acceleration because there is no radial acceleration for the center of mass. It's just going to be equal to alpha r. All right, so then if we have, then we know that alpha is at over r. So then this is just going to be, and we'll just call it a, our translational acceleration. So this is going to be a over r. All right, so then we're going to actually want to solve for r. All right, so then a is going to be t r squared over 1/2 m r squared. So then we see that our radiuses cancel. But the issue here, and maybe it's the order that the questions are asked, is that we actually don't know the tension force. And obviously that's going to be crucial to find the acceleration the way we set things up. And so what we want to do is actually do a sum of forces to help us find the tension. And that's often the case, that we want to not just to consider the sum of torques, but also consider the sum of forces, because the forces still matter. Now the forces don't look at the location of the force vectors in the same way the torque does. So it doesn't matter, for example, that the tension force acts over here and the gravitational force acts at the center. That's not going to affect the sum of forces. All that matters is that tension points up and gravitational force points down. All right, so let's look at the sum of forces in y acting on our yo-yo. And also, if we're going back to our steps, this right here would have been step 3 when we're using Newton's second law. All right, and I'll add a step 4 over here, which is use Newton's second law in translational form. Okay, and what that is going to look like, if we look, that's going to look at our sum of forces in y. All right, so F net y will define positive y as upwards. Okay, just like we have positive rotation is counterclockwise. All right, so that is positive theta. All right, so then F net y is going to be t minus mg equals ma. It's not equal to 0, because that would only be true if the yo-yo was at rest, and it's definitely not at rest, it's falling. All right, but that does tell us the very useful information that, oh, and also r, it's equal to negative mg, negative ma, so let's fix that, because it's accelerating downwards. But that gives us very useful information that t is going to be m, so it's mg minus ma, or m times g minus a. Okay, so that looks good. Make sure I do that correctly. So I move it over. Yeah, okay. So now I can substitute that in for tension, which means I will have to then solve for a little bit differently, right? So you can go up here, and we're going to have mg over 1/2 m, and then minus m a over 1/2 m. Okay, and so these cancel. All right, so then we're going to have that extra one, basically 2a term, which will then we'll have a 3a over there. All right, so we should get, let's see, so when we solve for this, let's see, yeah, so oh yes, okay, so algebraically, all right, let's make, I have to one more line down here. Right. Yeah, okay. So what this shows here, if we continue, is that we'd have, because this right here is going to be 2 or negative 2a, which I can add to both sides, so positive 2a there. All right, and then so I'm going to have 3a on the left-hand side. So 3a equals, well here I have g divided by 1/2, which is 2g, which simply tells me that a is 2/3 of g. Excellent. Okay, so a is 2/3 of g. All right, which is an incredibly clean result, right? Just really, really remarkable. All right, let's squeeze in the value here. So 2/3, 2 divided by, all All right, so 2 divided by 3 times 9.8. Can't do it in my head. Times 9.8. All right, 6.53. So 6.53 meters per second squared is the acceleration, the translational acceleration of our block. Okay? No, not our block, our yo-yo. Okay? So that leaves us only to find our tension, which we have over here. So we can actually just find that last calculation. Okay? So, technically we didn't need the tension value because we had it symbolic and we substituted it in. Although it may have made sense to ask for tension first. But then we can go ahead and plug in our numbers. So we'll plug in our known mass of 0.43. And notice it's the only time we've actually used that mass because it didn't affect the acceleration. And it shouldn't, because acceleration is a kinematic phenomenon. It is always independent of mass. And so that is no different here. The only thing that actually matters is the shape. So the reason we get the 2/3 is because it's a cylinder. That's where that comes from. And it really has nothing to do with the mass of the yo-yo. Or its radius, right, which just cancels out in every one of the expressions. Even in the tension, it cancels out. But the tension, right, a more massive yo-yo will create a bigger tension. So if we go ahead and just have 0.43 and then multiplied by 9.8 minus the value that we got for acceleration, okay, we get 1.40 newtons. Okay, so we were able to find the acceleration and the tension, but to do that we had to look at not just conservation of energy, but Newton's second law. We had to calculate torques, and we had to look at Newton's second law in the typical or the earlier seen translational form, as well as the more recently seen rotational form. Okay, thank you.